All right, exam 2 tomorrow. Based on the information you provided on Monday, it appears that this is the most favorable way by which we can offer you essentially 3 hours to work on this exam. So we'll stay open till 11:15, 11:30 if necessary. Tomorrow night, Flint 50 right over here. And for those of you who will take exam 2 tomorrow during the day or earlier in the day, I have noon to 6 p.m. available. So I ask that you select a 3-period block in there and give me a note to indicate when I can expect to see you. So you can start at noon, work to 3 p.m., start at 1 p.m., work to 4 p.m., 2 p.m., 5 p.m., 3 p.m. to 6 p.m. You tell me what you want. But this doesn't mean you get 6 hours. And if the overall performance improves considerably, as I hope that it will, then I'll see what I can do to provide extra time on all remaining exams. That'll be fun with the final, but I'll figure out something. I'll be damned if this administration is going to run my class. The needs of the students is what's supposed to run the class. Now, let's finish chapter 19 and then we'll jump into chapter 20, picking up from your point of departure following yesterday's discussion class chat. Silver oxide treated with ammonia. Notice the comparability of this to silver chloride treated with ammonia. In each case, we have a salt of limited solubility being driven in the solution by providing the opportunity for the silver ion component of the semi-soluble salt to react with ammonia and form the silver ammonia complex ion. Given that the silver ammonia complex ion is quite stable, we start by realizing whatever the solubility will be of silver chloride in ammonia, which we've already done, in this case silver oxide in ammonia, which we're just going to do, solubility of these salts got to be a lot greater than it is in straight water because of the complexation ability of ammonia with silver ion. Now, in calculating K for this, you know how to do that, so I'll leave the K calc part up to you. You'll get a K of 0.10. Now recall, when we looked at silver chloride being treated with ammonia, we got a K value of 0.0029. So after this I wrote so. What does the comparison of these K values suggest to you? Silver chloride treated with ammonia, K is 0.0029. Silver oxide treated with ammonia, K is 0.10. Which material is more soluble in ammonia? Is it silver chloride or silver oxide? Silver oxide. That's a bigger K. And with this, you'll calculate a solubility of silver oxide into 6.0 ammonia of 0.79. Now, what about silver oxide in ammonium nitrate solution? Now, as usual, whenever you deal with a system, chemical system, and whenever you are required to do something to the system and then analyze the system regarding the consequence of what you have done, we have to do all the time. Inventory, right? Yeah. Principal system inventory, all the time. If you are not always aware of the composition of the system, there is no way you can understand the chemistry which occurs in the system. And you can take that one to the bank for any chemistry you study. Now, for 1931. Silver oxide plus a system containing ammonium ion, nitrate ion, and water. Write the equation. Did you do it? Put it on your paper right now. Notice in this case, at the minimum, you're not starting with ammonia. But have we good reason to believe the silver oxide will certainly react with ammonium ion? At least preferentially relative to the reaction of silver oxide with water? Silver oxide with ammonium ion. Is that a more favorable reaction than silver oxide with water? You're damn right. Why? Why?
Ammonium is a stronger acid.
Ammonium ion is a stronger acid than water. And silver oxide contains the oxide ion. The strongest base listed in our acid-base table. So if any chemistry occurs in this system, it's certainly going to be this chemistry. Now then, when ammonium ion reacts with oxide ion, what are we going to get? Well, we're going to get ammonia. Now what else? Keeping in mind that in this system, the ammonium ion is in considerable excess. Ammonium ion reacts with oxide ion. Ammonium ion is in excess. What will be the products? Water and ammonia. So do we have again the chance to form silver ammonia complex ion? Because a product of this reaction is ammonia. So, can we well expect then, when the silver ion component of silver oxide goes into solution, it will not just dance around as silver ion, it'll react with ammonia and make the silver ammonia complex ion. Is that a good bet? Because the silver ammonia complex ion is a hell of a lot more stable than silver ion AQ. That's what the Kf value for the silver ammonia complex ion tells you. So let's proceed with this. And since you recognize that the other product of the ammonium ion oxide ion reaction is water, we can put water in there. But is there another product? What I want you to do is to look at this system carefully from a stoichiometry standpoint, realizing that in this system, the only way you can get ammonia molecules, which will then react with silver ion to make the silver ammonia complex ion, the only way you can get these ammonia molecules is by ammonium ion reacting with oxide ion. Okay so far? In a mole of silver oxide, as the formula tells us, 1 mole oxide ion, but 2 moles of silver ion. How many moles of ammonia do we need to react with silver ion to make the silver ammonia complex ion? Well, the formula for the complex ion tells us. Per silver ion complex, we need 2 moles of ammonia, right? And in a mole of silver oxide, we have 1 mole of oxide ion. So regardless of how much ammonium ion you put in the pot, per mole of silver oxide, how many moles of ammonia can you make?
1.
Per mole of silver oxide, how many moles of ammonium ion can you make? Oxide ion plus ammonium ion. Products, ammonia, water. But that's not an equation, because that's not balanced. I repeat the question. per mole of oxide ion on reaction with ammonium ion. How many moles of ammonia can you make? Write the reaction equation if it doesn't come to you by just thinking about it. Write it. Oxide ion plus ammonium ion. How many moles of ammonia? 2. But a mole of silver oxide contains 2 moles of silver ion. So of these 2 moles of silver ion, how many moles of silver ion can be complexed? 1. So what you need to realize is that in addition to making a mole of the silver ammonia complex ion, what else will be a product? Silver ion. Now, I went through this in a deliberate fashion because many students in the past have stumbled with this because they did not take the time to pay attention to the stoichiometry of the system. If you take a mole of this and you put in 1,000,000 moles of this, it doesn't make any difference. You're still going to be limited to producing 2 moles of ammonia, which means you can only complex 1 mole of the silver ion from silver oxide. So the other mole of silver ion is going to be in solution as silver ion itself. Now, the other part of this question, you can do the arithmetic. You can calculate K. You know how to do this kind of stuff. Silver oxide dissolving in an ammonium ion ammonia buffer. Now then, how do you think K for this reaction will compare to K for this reaction and K for this reaction, which we've already written here? K for this reaction. How do you think this reaction, from an effectiveness standpoint, compares to this reaction or this reaction regarding dissolving silver oxide? How do you think this reaction compares? Or put another way, which is really the same thing, which of these reactions has the greater thermodynamic drive toward getting silver oxide to dissolve? This one? This one? This one. Which of these reactions does the best job of getting silver oxide into solution? The top one, where we got an abundance of ammonia, the second one where we have an abundance of ammonium ion, or the third where we have ammonia as well as ammonium ion in abundance? Which is the best one? Third one. Why?
2 different sources.
This is a 2-part issue. To get silver oxide to go into solution by the methods we are considering, we want to do 2 things, don't we? What are the 2 things we want to do to silver oxide? We want to complex it and create the silver ammonia complex ion. Okay? What else do we want to do? As illustrated by this middle of the board reaction. We want to murder oxide ion, don't we? Ammonium ion murders oxide ion, but it doesn't complex silver ion, because ammonium ion is not ammonia. Ammonia complexes silver ion, but it doesn't clobber oxide ion. So if I start with a system that contains both ammonium ion and ammonia in abundance, then I'm ready to complex and clobber oxide ion, all ready to go. Effectively a double attack. Guaranteeing that this treatment is far more effective at getting silver oxide to dissolve compared to this treatment or this treatment. So when you calculate K for this system, what kind of a value will you get magnitude-wise compared to this K or the K for this, which you are to determine? What? A much larger K, you betcha. What is the K value? I don't know. I've got it written here someplace. Ah! Not bad. 0.10, 3 times 10 to the 8th. This is what thermodynamics is all about. Now then, the remaining part of chapter 18 invites you to think about all the stuff we've been doing so far. And put your thoughts together. Put your knowledge of chemistry, which you should have at this stage of the game, to use, and do the thing which is most difficult for students to do. Write equations for reactions. This is what textbooks never ask you to do. The most important part of chemistry, and they skip right over it. Because not only is it the most important thing to do, given that chemists, for the most part, run reactions and study reactions, it's also the hardest damn thing to do. That's why the textbooks skip over this. And that's why the textbooks do such a miserable job for general chemistry. That's why they flunk. Now, acid-base chemistry, chapter 18. Semi-soluble salt chemistry, chapter 19. To which we've now added the possibility of forming complex ions. And that's it. That's it. We've looked at the whole ball of wax regarding the chemistry of species in water solution, with one exception. I shouldn't have said that's it. That's it, but one. The one we still have to do. And that's coming at us in chapter 21. It's called redox chemistry. Did you learn anything yet about redox chemistry? Did you do experiment 5, part 1 in 45 laboratory? Well, for those of you who did and thought about what you were doing, you've already learned something about redox chemistry. Redox reactions are arguably the most important category of chemical reactions. All the reactions which take place in the body to give us nutritional energy from the consumption of food, all redox. All reactions, other than nuclear reactions, which liberate large quantities of energy, like burning gasoline in your automobile. All redox. Important reactions, very. That's still to come. But based on acid-base chemistry, based on semi-soluble salt chemistry, based on the tendency to form complex ions, we can recognize that for question 1932, part A, based on the information given, based on what you ought to be able to recognize from what you see on our information sheet. Copper sulfide is a daggone stable stuff. So if I take this and treat it with H2S, you're going to prepare this ion with laboratory work in assignment 6. Anybody assignment 6 yet? 46L. Cuprate ion. an ion which can exist only at very high pHs. Hydroxide ion molarity must be extreme to make this thing. Well, if I hit this with H2S, then I have every reason to believe I'm going to clobber this ion, because I'm going to murder hydroxide ion, because that's an acid. And not only in so doing, I will provide a source of sulfide ion. So I shouldn't be surprised to find out that this converts to this, which is a damn stable stuff, a whole lot more stable than this. Calcium hydroxide plus ammonium ion bicarbonate. We've already done this kind of stuff. Ammonium ion kicks the hell out of hydroxide ion, and bicarb ion provides a source of carbonate ion. So what do I expect to be for this system as the calcium ion containing product? Calcium carbonate. Calcium carbonate plus water establishes an equilibrium. An equilibrium with a very small K value. 1.3 times 10 to minus 12, given that we've calculated this K value and used it a number of times during in-class analysis of calcium carbonate in water solution and its solubility. If I take this equilibrium system and I treat it with 1 molar ammonium sulfate, what reactions do I expect to take place? Reactions of consequence. I'm not talking about ammonium ion being diluted with water. That reaction does occur when you do this, but it won't be a reaction of consequence. Would I expect to do something to this? What is the something I would do to this? Tell me the formula for this system, those ingredients of this equilibrium system, treated with this. Tell me the formula for the principal calcium ion product of this treatment. What is it? You betcha. Will I expect a reaction with this stuff? Will it be large extent or small extent? What will react with that stuff by this treatment? Ammonium ion, won't it? Does ammonium ion react with bicarb ion large extent or small extent? Large or small extent? We did this. Large or small extent? Small extent. Ammonium ion bicarb ion products, H2CO3 quote unquote, and ammonia, small extent. How about reaction with hydroxide ion? Large extent. So a lot of reactions go on here. But the one of main consequence will be the conversion of calcium carbonate to calcium sulfate. Do you think this treatment will result in a reaction which has a very large K value? It's not easy to answer, but this is chemistry. And chemistry is not easy. I like these textbooks with which to advertise themselves on the basis of. Use this book and you will be a master, you will become mastering chemistry. There ain't no son of a bitch in this world who masters chemistry. What is this garbage they do? The best chemist in the universe is hardly a master of this subject. It's too much. It's too difficult. It's too complicated. And they tell these lies to folks like you, or to people who are of a mind to buy this book. Use this and become a master of chemistry. The amount of chemistry which I know can be inscribed on the head of a pin on a comparative basis. It's amazing the stuff that goes on in this world. Always keep yourself aware. Always think. Don't take anybody's word for anything. Now, there's one quality that you must have if you're going to be a good scientist, and that's be skeptical. Be very skeptical. Notice that in this system, you're converting this to this, but this is of lower solubility than that, isn't it? But you are reacting ammonium ion with hydroxide ion, that's a large extent. So you've got different issues going on here which affect the ultimately affect the magnitude of the K value for this system. Calculate the K. See what you learn from it. Now, part D is nothing but what we have up here. Question 31. There it is. I went too far with that. Right here. Okay? And then part E is also question 1931. If you read question 1932 parts D and E, you should see the immediate relationship to what we have here. And then part F says, if I take the equilibrium system established by taking silver oxide and treating it with ammonium ion and ammonia, which will effectively convert the silver oxide to the silver ammonia complex ion, and not have any silver ion in the system, but treat that equilibrium, silver oxide treated with ammonium ion and ammonia, producing silver ammonia complex ion as the only silver containing product, and treat this with H2S. What am I going to get? That stuff. Because that stuff is a heck of a lot more stable than silver oxide. It's a heck of a lot more stable than the silver ammonia complex ion. It's a heck of a lot more stable than silver chloride. The information on our information sheet tells you that. So, if you pay attention to the system in terms of inventory, you have a chance to make correct decisions regarding the outcomes of each of these systems. So we go to chapter 20, which you were talking about in detail yesterday, and I hope you recognize that most of chapter 20 is in fact just a review of what you already did in Chemistry 2045 on the chapter called Thermochemistry. But with one very important and additional consideration. That being, what you really want to know about any reaction is, can it go under the conditions under which it's being studied? And if it can go, the fancy word for it is spontaneous. And if it can't go in the indicated direction, non-spontaneous. But if you have got all the components of the system present, reactants as well as products, and it's not at equilibrium, then the system can either go left to right or right to left, thermodynamically speaking. And if it can go right to left, then I've coined the term anti-spontaneous. It goes, but in the direction opposite to the way you've written the reaction equation. And the spontaneity factor most commonly used by chemists is delta G. If we put a sub R in there, it means for the reaction. And if delta G is computed by using this very powerful and important equation, which puts together the two fundamental thermodynamic puzzle parts of any system studied thermodynamically, the change in enthalpy and the change in entropy, with the change in entropy multiplied by the temperature at which the system is being studied in Kelvin. You can find out if the thing is spontaneous or not. For a spontaneous reaction, what kind of sign you get on delta G? Minus. And delta G0 corresponds to the same consideration, except under a very specific set of conditions, which we'll talk about rather extensively when we get to chapter 21. Specifically, what conditions? What conditions? What does the superscript 0 denote? Standard state conditions. Did you learn what standard state conditions mean? If you're in the laboratory and I tell you to run a reaction under standard state conditions, what conditions will you establish?
25 degrees Celsius.
Don't tell me anything about temperature, because there ain't no such a thing as a thermodynamic standard temperature.
1 atmosphere.
Concentration of 1 molar.
All solute species for solution studies are to be present at what molarity? 1. That establishes standard state for solution species, solutes. How about gases? 1 ATM or 1 bar. But there's not much difference, because 1 ATM is 1.01 bar. And I think most of the data in the notes is still corresponding to measurements made in atmospheres. I'm waiting for the National Bureau of Standards to put out a table where they say, now everything's in bar. Then I'll change to bar. But I'm going to take all that damn data and do the arithmetic to convert everything in there to bar. But it's really only of consequence, atmospheres versus bars, when you're dealing with systems with gases. Now then, in a system, we can have solutes, 1 molar. We can have gases, 1 atmosphere partial pressure for each gas in the system. So if you've got 2 gases in the system, total pressure on the system is 2 atmospheres. 3 gases, 3 atmospheres. At least if the system is under standard state conditions. And what's the other possible component of a system? Pure stuffs. Liquids, solids. And by definition, they're in the standard state, because they have activities of unity. More on this activity stuff. But we need not be concerned with that at this stage of the game. So if you are dealing with a reaction system that contains 1 or more pure solids or 1 or more pure liquids, just put them in. They're in the standard state. But in the required mole quantities for the reaction as you are considering it to take place. If you want to make a mole of this, then you need enough reactants to make a mole of this, whatever the case might be. Now then, some of you got to talk about this yesterday, some of you did not. Diamond graphite. So please, right now, whether or not you talked about this, open up table 1. That's the thermodynamic properties data table at the end of chapter 20 in the notes, and find carbon in that table. Specifically, with this consideration, we want you to realize why carbon graphite is standard state carbon rather than carbon diamond. Because carbon graphite is thermodynamically more stable than carbon diamond. Hard to believe, isn't it? Because I'm sure you well know that diamonds are a hell of a lot harder than graphite. So how can graphite be more thermodynamically stable than diamond? Maybe I should just ask those of you who heard this conversation yesterday in discussion class to come forward and do the explanation. You want to do it? That's all right, I'll do it. Now then, models. This conglomeration is a diamond sample. The model is small, my apologies. And if you wish to come up after our talk and look at the model more closely, please be my guest. But if you can, focus your attention on this carbon atom. their immediately connected atoms are of opposite color, just so you can more easily visualize the model itself. Notice this carbon atom. Its nearest neighbors to which it is covalently connected, 1, 2, 3, 4 carbon atoms. So you can write a picture on the board. And if you look at the lattice in an expanded fashion, you'll see every carbon atom in the lattice shows this property. It's covalently connected to 4 nearest neighbor carbon atoms in what kind of a geometric pattern? Tetrahedral. How's this carbon hybridized? How's every carbon atom hybridized in the diamond lattice? sp3. So you recognize that the carbon-carbon bond order, covalent bond order for carbon and diamond is 1.0. Okay? 4 covalent bonds to every carbon atom. Then you look at the graphite lattice. Because if it is true that graphite is more thermodynamically stable than diamond, then the doggone covalent bonds, carbon-carbon covalent bonds in graphite, strength-wise, must compare how to the carbon-carbon covalent bonds in diamond? Stronger. So you look at the graphite lattice, and you see that to examine the graphite lattice, you must assume 2 different perspectives. Viewing the lattice this way or viewing the lattice this way. So let's view the lattice this way and look at this carbon atom as a reference. And you see that this carbon atom has only 3 nearest neighbor carbon atoms, which is shown by every other carbon atom in the graphite lattice. For carbon atoms that are together by way of being in the same plane, the same geometric plane inside the lattice. So we'll put that on the board. With a question mark, because we've left something out from this picture. What kind of geometry do you see here? Trigonal planar. What kind of hybridization do you associate with trigonal planar? sp2. So we can recognize by looking at the geometry of the carbon atoms in a plane in the graphite lattice that they're sp2 hybridized. Now, did you also learn in Chemistry 2045 that carbon in each and every even electron species or substance? What's this term mean, even electron? The sum total of valence electrons for the stuff is an even number. That's all it means. Is carbon such a species? Does carbon have an even number of valence electrons? How many valence electrons for carbon? 4. Don't count the 1s2 pair from energy level number 1. For each and every such carbon atom, with the exception of 1 species only, and that's CO, carbon is always associated with a total of how many covalent bonds? 4. So we left the covalent bond out from this picture. Should I put it here? Maybe I should put it here. Maybe I should put it here. Does it matter? No, why not? Because this stuff has resonance. So the carbon-carbon bond order for the carbon atoms in graphite is 4/3. And here again is a case which shows you why. You cannot pictorially represent resonance accurately. You just have to know about it. Because there's no double bond, carbon-carbon double bond, and carbon-carbon single bonds in this stuff. All the carbon-carbon bond lengths are shorter and stronger than they are in diamond, but all the carbon-carbon bond lengths are equal in strength and length. All shorter, stronger, and equal in strength and length. That means delta H, F, 0. Standard state conditions. What's the F mean? Formation. That means delta HF0 for this compares how to delta HF0 for this? When you talked about delta H in 2045, did you recognize that the higher the enthalpy of a stuff, the more stable or less stable it is? The higher its enthalpy. More stable or less stable?
Less.
More or less? This is another thing I like about textbooks. They got you doing all these calculations with Hess's law, and you don't know what the hell enthalpy is. Enthalpy is a measure of bond strength. The stronger the bonds, the lower the enthalpy. The stronger the bonds, the lower the enthalpy. So which one of these has the lower enthalpy? Graphite. So look at the table and see that delta HF super 0 for carbon diamond is a positive number, isn't it? It has a higher enthalpy than carbon graphite. Because when you convert carbon graphite to carbon diamond, you are weakening bonds. You're going from 4/3 carbon-carbon bond order to 1. Now comes the other part of the puzzle. Entropy. If it's also true that graphite is thermodynamically more stable than diamond, we should well expect that graphite has a higher entropy. Look at the table. Does it? Now, entropy is kind of a strange term to define, but it does measure or reflect bond strengths in a direction opposite to that of enthalpy. Weaker bonds, higher entropy. But we've already said the damn carbon-carbon bonds are stronger in graphite, so how can the bonds be weaker? Well, we haven't looked at all the bonds yet in graphite. What about these bonds? The bonds that connect this plane of atoms to this plane of atoms. Why is it that you can take your graphite pencil and push it across your paper and leave behind a stream of carbon atoms? If you want to write your notes with a diamond pencil, what you're going to have is a bunch of scratches. Right? You're not going to destroy any carbon-carbon bonds. And when you write with a graphite pencil, do you destroy any carbon-carbon covalent bonds? Do you destroy carbon-carbon covalent bonds when you write with a graphite pencil? Absolutely not, none, zero, zip. What you do is to take a plane of carbon atoms and tear it apart from the next adjacent plane of carbon atoms, because these planes of carbon atoms are held together by the weakest type of bond interaction shown by substances. What is this weakest type?
Dispersion.
London dispersion forces. That's what you're tearing up when you write with a carbon graphite pencil, and that's why the graphite lattice is much weaker than the diamond lattice from an overall lattice string standpoint, and that's why graphite has a higher entropy. Pick it up from this point next time.